Okay, did you enjoy the ammonia program where we plotted out the bond length at minimum energy? Well, the script was pretty short, and maybe you think, and it would be correct, that there's got to be more code behind this because it's a quantum chemistry problem. And quantum chemistry involves quantum mechanics, and quantum mechanics involves a lot of math. So somewhere along the line there had to be some more stuff. So what I'm going to do to start with is look at the resources that this program uses to do its calculations. Okay, I've got my cursor up there, and as you notice, as I hover over these items, it gives descriptions of what's going on. It makes it really handy. What can we say about this? This is for math, and this is for plotting. Now, let's get down to the Qiskit stuff. Qiskit algorithms. Library of quantum algorithms for quantum computing. These algorithms can be used to carry out research and investigate how to solve problems in different domains on simulators and near-term real quantum devices using shallow circuits. See, so we're quantum circuits. So this is very specific to what's going on here. The library includes some algorithms, for example, the NumPy minimum eigensolver, which take the same input as their quantum counterparts, but solve the problem classically. This has utility in the near term. Oh, blah, 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 blah. Let's see what some other things down here are. Qiskit nature. Now this is the natural science business, and this is real physics, whereas the other was the mathematical constructs that we have to use. And this is the thing that I'm interested in, is the PYSCF driver. SCF. I wonder what that stands for. Let's see what's going on here. Approximate tetrahedral geometry. So these are the nitrogen H bond lengths. And you say, why bond lengths? Why 3? Well, it's NH3. And here's the geometry of it. This 107 degrees is the geometry between all the different bond lengths. And this one's simple. It's just an array. So that's the array where we store all the different energies. Each time we go through this loop, and you say, well, for R and RS, what was RS? RS was the 3 bond lengths. Here's the 3 hydrogen atoms with their coordinates, X, Y, and Z. And notice this R value. That's going to be important in the next 2 hydrogens. The hydrogen here is a sine of theta and cosine of theta, and this one down here is also sine theta and cosine theta for the X and the Z coordinates. Molecule string. This is the nitrogen, hydrogen, hydrogen, hydrogen. Here's where we establish this driver, which will have the molecule string in there to work with it down here. So where did the molecule string come from? Well, it's right up here. So all of these were just to load up, so it's all leading to this character right here. This character is going to take a significant amount of discussion here because it's so important. Stepping away from the code for a while, here's where I need to go. And I need to go to another playlist. And that playlist being specifically quantum chemistry that supports what we're talking about. To give you an idea, here is classical chemistry. That's what we were just about to get started with. Here's that SCF and Hamiltonian construction, which is the quantum mechanical energy operator. Then the quantum algorithm, and this is a hybrid between classical and quantum computing methods. And then you know the result, we get the bond energy curve. After this, go to the playlist, if you dare, of quantum chemistry for quantum computing.